Hello guys, welcome back to this channel. On this channel we're talking about the classification of physical quantity in physics. So if you have not subscribed to this channel, head to the subscribe button, like this video for more. So back to the video, we have classification of physical quantity. Number one, we have fundamental. What is fundamental quantity? Can be defined as the basic quantity in physics from which other quantities are got. That means without this quantity, without fundamental quantity, we can't have other quantity. That means look at the examples, look at the major 1, 2, 3, 4, 5, 6, 7. These are the 7 standard fundamental quantity we have in physics. So let's define fundamental quantity. These are connected to these are basic. This means that they are quantity. These are basic quantity in physics. That must be noted. In physics, from which other quantity are gotten from. That must be noted. So we can define fundamental quantity. These are basic quantity in physics from which other quantity are gotten from. And this must be noted that when you hear the word quantity, it means that it can be measured. So these are the basic 7 fundamental quantity we have in physics. They are the standards and the approved one. So let's go for the SI unit and dimension, because in today's video I'm talking about fundamental quantity, derived quantity, and dimension. So for the first one, we have mass. What is the SI unit for mass in physics? Is kilogram. This, let me just use this abbreviate to be kg, which means kilogram. And the dimension for mass is m. That must mean that the dimension for mass is m. Then for length, the SI unit for length is meters. That must be noted, which can be noted as m in the question to abbreviate it. And the dimension is n. L. That must be noted. That is the dimension for length is m, and the SI unit is meter. For time, the SI unit for time is seconds. That must be noted. And to make it, abbreviate it, we use S to represent seconds in physics. Then for the dimension for time is T. That must be noted. Then we have current. The SI unit for current is ampere. Ampere. That must be noted. Then to abbreviate it, we use letter A to represent it. The dimension for current is I. Dimension for current is I. The SI unit is ampere. For temperature, the SI unit for temperature is Kelvin. That must be noted. That the SI unit for temperature is Kelvin, which can be represented with letter K. The dimension for temperature is like a theta. This is dimension for temperature. Then for light intensity is candela. So candela. And light intensity don't have a dimension. So you don't have a dimension. That means that when you are given a question to look for the light intensity dimension is dimensionless. For amount of mole, the SI unit for amount of mole is mole, which can be represented with letter M, like number of mole as its SI unit as mole. While for dimension, you don't have dimension. So you can be taken from this video lesson that light intensity and amount of mole from fundamental quantity are dimensionless. So let's go to the next part on this video lesson on derived quantity in physics. We have this derived quantity. From the word derived, it means it was gotten from something. That means to break it down simply, you can therefore say that derived, just derived alone. From the word derived means got from something. So let me explain what are derived quantity. These are quantity in physics which are gotten from the mathematical combination of fundamental quantity. That means derived quantity are combination of fundamental quantity. So let me say that derived quantity, these are quantity, these are quantity, these are quantity, these are quantity gotten from the mathematical combination of fundamental quantity. This is the definition of derived quantity. So let me go again. These are quantity gotten from the mathematical combination of fundamental quantity. Very simple, it's not hard. So I left this slide for a reason, because looking at it, I told you that these are the 7 major fundamental quantity that we have, the standard. So we have examples of derived quantity. I will give an example. Number 1, let me give an example. We have velocity, which can be gotten as the change in displacement. So change in displacement with time, so it will be over time. There are others like the likes of acceleration, density, Young modulus, compressibility. So I will take a practice question on this, because after this that quantity we'll move over to dimension. In dimension, on the next video lesson, on the next part of this video, you understand properly facts about derived quantity. So let's move over to dimension in this video lesson. Okay guys, back to dimension. First of all, before we analyze this question being given here, let me give you a bit tips about dimension. Dimension can help to check if the formula is correct. So one of my friends gave me a question in application of dimension. So after solving this, we'll solve the question being given by the person for me to solve. So first of all, we have to look at the dimension of the following: mass, time, length, current, velocity, acceleration, and the others. So first of all, I told you that the dimension for mass is just m, so you don't need to solve anything, just m. Dimension for time, I told you that is t, 30, and dimension for length is L. Dimension for current is I. Dimension for velocity, we have to solve it. First of all, what is the formula for velocity? Velocity can be defined as a change of displacement with time. So displacement with what? Displacement with what? With time. So what is displacement? Displacement has to do with like a distance, and the SI unit for displacement, or let me say meters, because it has to do with distance. So it can present with L. So when you want, distance comes with length. So whatever say that the dimension for the displacement will be L. So velocity equals dimension for displacement is L over dimension for time, I gave you is T. So T over T. So to solve this has to come up. It will now be therefore L_t inverse. So this thing come up, I got a lot of indices. It will go up to be inverse. The dimension for velocity is L_t inverse. So let's solve for the velocity, dimension of acceleration. Okay guys, let's solve for the dimension of acceleration. And acceleration is the change of velocity with time, velocity with time. And earlier I give you the dimension of velocity, which was L_t inverse. So that was say therefore dimension of acceleration equals to the dimension of velocity was L_t inverse over t, which is the time. So taking this t upward, it will now be therefore L_t inverse. This t come up, it will be -1, then L_t minus times minus is plus. So 1 plus 1 is 2 minus. So the dimension of acceleration is L_t inverse raised to power 2. So the dimension of acceleration is L_t inverse raised to power 2. So let's look for the dimension of electrical charge. The dimension for electrical charge from Faraday's laws of electricity. The first law, it states that the quantity of electrical charge is equals to it, which is the time, which is the current and time. So it can be deduced that to get the dimension for electrical charge, because for you to get dimension you must know the formula. Formula for electrical charge is Q equals it. So, and this is current. Dimension for current is I. Therefore, I. Dimension for time is what? Is T. So dimension for electrical charge is it. Very simple. It's not hard. So equals to what? it. So let's look for the dimension of density. Dimension of density. Density, the formula for density is mass over volume. So with this, we can get the dimension of density. Okay, looking at this table I gave, say that the dimension for mass is m. So therefore, the dimension for density can be deduced that the mass, dimension for mass is m over this volume. Volume, the SI unit for volume, although I don't give it in this table, is so. Note that the SI unit for volume, SI unit of volume, or let me say SI unit of volume is L raised to power 3. So note that the SI unit for volume is L raised to power 3. So we can therefore apply this knowledge here by saying L, which is the length, raised to power 3. So to get the dimension, it has to come up to be therefore L raised to power minus 3. So the dimension for density is L raised to power minus 3. Dimension for density is L raised to power minus 3. So let's look for the dimension of strings. Is extension over length. So we can therefore say that string is extension over length. Extension is measured, the SI unit for extension is length. So therefore say therefore extension is equals to length over dimension for length. For length is L2. So L cancel L. So can therefore say that strain has, or let me say the word, zero dimension. So strain don't have a dimension. So when we are given a question to solve for the dimension of strain, it has no dimension. So let's look for dimension of, first of all, we have to know the formula. Formula for work is force times distance. So let me use the first letter to represent it. Force, letter F, times what? Distance. Okay, force can be broken down with this formula that said that force is equals to ma. So note that the formula for to get the formula connecting mass, area, mass, acceleration is F equals to ma. So let us say that force is ma. So ma, therefore force is ma times d. So this is mass, acceleration times distance. The dimension for mass is m. So let us say m, therefore m dimension for acceleration I gave you earlier is nt raised to power minus 2. So nt raised to power minus 2 times distance. Dimension for distance, or can be length, is L times L. So looking at it, we have m here, m here. I'm going to do a lot of indices. There's an invisible one here, there's an invisible one here. Which one plus this one, take the base, take one base by saying therefore m L, there's an invisible one here and an invisible one here. There's same base, take one base. 1 plus 1 is 2. So L raised to power 2 T raised to power minus 2. The dimension for work is L raised to power 2 and T raised to power minus 2. So dimension for work will be M L raised to power 2 T raised to power minus 2. So let's get the dimension for power. Guys, we have to look for the dimension of power. The only formula to solve this, not only the formula for power, which is work done, or let me say work over time. So we have to know the dimension for work and time. I can solve this, but since we already have it in the table, so there's no need for to solve it. Let's just substitute it into the formula by saying dimension for work. Therefore, dimension for work I gave you earlier, I will solve it. Is on m L raised to power 2 and T raised to power minus 2 over time. So the dimension for time is t, letter t. So therefore, to solve this further, to break it further, m, we have L here, so it will be L raised to power 2. We have t here, this one minus 2 times T raised to power minus. So if you bring this one, it will be an inverse form. Looking at this, they have the same base. They have the same base, t. Let's say that m L raised to power 2, take one base. I go to the laws of indices. We add the power by saying that, let me put it here, minus 2 plus open bracket minus 1 close bracket to be minus 2 minus 1. Minus 2 minus 1 will give us minus 3. So this, the t is set for minus 3. So dimension of power will be m L raised to power 2 and T raised to power minus 3. T raised to power minus 3. So let's get the dimension for impulse. First of all, let's do the formula for impulse. Formula for impulse is force, let's use the letter F to represent it, times time. Okay, let's look at the dimension of force and time. We have dimension of time here, but we don't have dimension of force in the board. So to calculate it, remember I told you that earlier that force is equals to ma. So with this, we can get the dimension for force. Force equals to ma, which is m. Therefore, ma times time. This time here, force equals to ma. Dimension for this is mass. Dimension for mass is m. So m times dimension for acceleration gave here earlier, it was l raised to power L_t raised to power minus 2 times t, or the dimension for time is letter t. Okay, to solve this further, therefore m, you bring your ml, there is t here, there is same base. I get the laws of indices. It will be minus 2 plus an invisible one here plus 1. Okay, minus 2 plus 1 will give us minus 1. So therefore, ml raised to power t raised to power minus 1. So the dimension for impulse is L, then t raised to power minus 1. So let's look at the dimension of force. We did it here. So, but I want to solve it fresh. So you understand dimension. Okay, guys. To get the dimension of force, told you that the formula for force, kinetic force, is ma. So therefore, we can therefore say that force equals mass times acceleration. Dimension for mass is m. So therefore m times dimension for acceleration, we saw it earlier, it was l t raised to power minus 2. So therefore the dimension for force is m l t raised to power minus 2. So therefore the dimension for force will now be m, let me take it upward, to be m l t raised to power minus 2. So let's look at the dimension of pressure. Okay, guys, let's get the dimension for pressure. First of all, what's the formula for pressure? The formula for pressure is force over area. So force over area is the formula for pressure. This must be noted. So let's look at the dimension of force. Earlier we did a dimension of force in this table below is therefore is m l t raised to power minus 2 over area. And note that to get area is length times breadth. So length times breadth, and both of them is measured in meters. So we can therefore say that m l t raised to power minus 2 will now be, since they are both measured in meters, and it connects, this meter connects length, can therefore call them length, and length times length, there's an invisible one here. We take one l, add the power according to the laws of indices, it will be l squared. So therefore it will now be l squared. Okay, let's make it more easier. We have l here, we have l here. In this l, cancel out 1 here. We will therefore have there's no l again, it has gone, t raised to power minus 2 over l. If this l is to come up, we will therefore now have l raised to power minus 1 and t raised to power minus 2. So this is dimension for pressure. So let's at the table below by saying that dimension of pressure is m l raised to power minus 1 and T raised to the power minus 2. So this is dimension for pressure. Let's look for the dimension of stress. Okay guys, let's look for the dimension of stress. First of all, let's know the formula for stress. The formula for stress is force over area. So you may be wondering that pressure and stress has the same formula. So if we solve it, we will still get the same thing here. So let me solve it to be sure, to show that stress and pressure has the same dimension. The dimension of force earlier in this table below is M. Therefore, M L T raised to the power minus 2 over area. So you learn that area is length times breadth, both in meters. We can therefore say that L times L. According to the laws of indices, there's an invisible one here. Take one of the base, L. 1 plus 1 will be 2. We can therefore say that L square will be for area, dimension for area. So therefore, if one L take one L here, is 1 here. So it will be M. If this L is to come up, it will be L inverse, then T raised to the power minus 2. See that both pressure and stress has the same dimension. So it can be that dimension for stress will be M, L raised to the power minus 1, and T raised to the power minus 2. So let's look at the dimension of Young modulus. Young modulus. The formula for Young modulus is stress over strain. That is the formula for Young modulus. So we can get the dimension. So breaking it further, the formula for stress is force over area divided by the formula for strain is extension over length. So if we are to reverse this in a fractional way, it will now be equals to F over A will now be, this L is to turn it inversely to be times L E, because to make this proper to solve this length, you have to reverse the fraction and put a multiplication sign. I told you earlier that extensions measure in length. So we can therefore say that let E equals that means let extension equals to length. So force times L over area extension is equals to L. So L cancel L. Can therefore say that force over area. And earlier I told you that to get your dimension for force in the table below we have is M L T raised to the power minus 2 over area is length times breadth. So length times breadth, both are measured in meters. So we can never say that length times length, laws of indices, take one base. If you say one is here and if you say one is here, add it to be 2. So L square. Let's cancel this L here. We have one L here. To make it take the L upward, it will therefore means that L inverse T raised to the power minus 2. Looking at it, pressure, stress, and Young modulus has the same dimension. That must be noted. So if a question is given you and asks you that which of the following has the same dimension, you see pressure there, you see stress there, and you see Young modulus. Note that pressure, stress, and Young modulus has the same dimension. So if a question is given to you, you need to solve for this, or if you have to calculate, solve for each of them. Solve for one of them. The three of them, pressure, stress, and Young modulus, has the same dimension. That must be noted. So the dimension for Young modulus is L raised to the power minus 1 and T raised to the power minus 2. Look at it. The three of them has the same dimension. So let's solve for the dimension of this one, which is, I call it centrifugal force. The space was very, so I have to activate it to be centrifugal force. Let's look at the dimension of centrifugal force in this video lesson. The formula for centrifugal force, it has a formula, but let me use one of them. That will be easy. Is m v square over r. So that means that the formula for centrifugal force, the centrifugal force is m v square over r. Okay, this m is your mass, v is your velocity, r is your radius, can be called distance. So let's look at the dimension of it. Dimension for mass is m, so m, therefore m, multiply. Dimension for velocity I gave you earlier is L t to the power minus 1. So in the bracket, L t to the power minus 1 all squared over this r is called a radius, can be called distance related to length over L. So opening this, like using square this 2 to open the bracket, it will be L, therefore L squared t to the power minus 2 over L. So this L, we're going to this L square is out already. We now have L. There's L is remaining here, so an L remaining here. So L t to the power minus 2. So the dimension for centrifugal force is L t to the power minus 2. So M t to the power minus 2. So the dimension for centrifugal force is m t to the power minus 2. So let's look for the dimension of kinetic energy. Okay guys, let's for the dimension of kinetic energy. So let's look, the formula for kinetic energy is half or 0.5 times, or let me say half mv square. So this is the formula for kinetic energy. And note that in dimension, any number, it can be half, it can be 1, it can be 2, is always equals to 1. So be it any number, it is always equals to 1. So therefore, we can say that this half is equals to 1. So 1 times the formula, which is mv square. Okay, we still get back mv square. Okay, this is mass, this is velocity. The dimension for mass is m. So we can say that m times dimension for velocity, let me put in the brackets, is L t to the power minus 1 all squared. Opening the brackets with these 2 here, it will be m, therefore it will be m, then L to the power 2 and t to the power minus 2. So the dimension for kinetic energy is m square t to the power minus 2. Let's put it here. It will be m L square t to the power minus 2. That's the dimension for kinetic energy. So let's look at the dimension of potential energy. Okay guys, let's look at the dimension of potential energy. The formula for potential energy is mgh, where m is the mass, g is acceleration due to gravity, and h is your height. So therefore, to get this dimension for m, which is mass, therefore dimension for mass is m and g is acceleration due to. So we can therefore say that a, which is acceleration, is equals to acceleration due to gravity. They are the same SI unit, so they have the same dimension. So times from the table below, L t to the power minus 2 times what is h? H is height. The SI unit is meter, so it will coincide with L, with length, which will be L. So L. So we now have therefore M. Look at L. So take one. Put a lot of indices. There's an indivisible one. There's an indivisible one. Add it. 1 plus 1 is 2. And T to the power minus 2. So the dimension for kinetic for potential energy is M. L to the power 2 and T to the power minus 2. So M. L 2 and T to the power minus 2. So looking at it, you can see that potential energy and kinetic energy and potential energy has the same dimension. That must be noted. So let's look for the dimension of viscosity. Okay guys, so let's look for the dimension of viscosity. What formula for viscosity? The formula for viscosity is tangent stress. Let me say tangent, let me use the word, let me abbreviate it. Tangent stress over velocity gradient. So let's say V for velocity gradient. When you hear the words gradient, it has to do with per distance or per length. So therefore, tangent stress, for the formula for tangent stress is force over area divided by velocity gradient is velocity. I told you earlier that when you hear the word velocity gradient, it has to do with per distance or per, let's say per length. Okay, by turning this upside down, we will therefore have to introduce a multiplication sign to be FA times M over V times length with force times length over AV. Force over area is stress. So the dimension for stress in the table is M L raised to the power minus 1 and T raised to the power minus 2. That is the dimension for stress, which is force over area. We have length times length. What's velocity? The dimension for velocity in the question, in this table, is L T raised to the power minus 1. So looking at this L here, we cancel the M here. So we now have M. There's L here, L to the power minus 1. Then there's T here, T minus 1. This one is to come up, it should now be T1 because the reverse of inverse will give you that thing to be 1. So there's minus 2 here plus 1. Therefore, we now have that M L raised to the power minus 1, then T minus 2 plus 1 will give us minus 1. So the dimension for viscosity is M L raised to the power minus 1 and T raised to the power minus 1 and T raised to the power minus 1. So let's look for the dimension of the following, which is molar gas constant. So let's look at the dimension of molar gas constant. What is the formula for molar gas constant? Let's say P V equals N arrow T, where P is your pressure, V is your volume, number of mole, and molar gas constant, which is this arrow. So let me describe the formula. We have both sides by arrow by NT, N cancel N, T cancel T. Molar gas constant will now be arrow is equals to PV over NT. Note that number of mole is equals to 1. So number of mole is equals to 1. So we can therefore say that molar gas constant, this pressure, the dimension of pressure we saw earlier is from the table L raised to the power minus 1 and T raised to the power minus 2. From the table, this is volume. I told you that the dimension for volume is L cube. So therefore, we now have L raised to the power 3 over this n is 1 times the dimension for pressure. I gave it earlier in the fundamental quantity, which is here, is theta, like a theta. That is the dimension for temperature. So T, that is theta, that is T, which is pressure, theta. So we now have M as the dimension. This L1, L is power minus 1, laws of indices plus 3 in the power. Then T is power minus 2. This theta has to come down with theta inverse. Okay, we now have L minus 1 plus 3 will give us plus 2, which now be L square 2 T inverse of 2 theta inverse. So the dimension for molar gas constant is L square 2 T inverse theta inverse. That is still T inverse of L square 2. So the dimension of molar gas constant is L square 2 T square minus 2 and theta inverse. So that's the dimension of gravitational constant in this question. In this video, gravitational constant. From laws of Newton, laws of motion, the formula collecting it is F, which is the force, is equals to G, gravitational constant, m1 m2 over distance squared. That means distance apart them squared. So looking at it, let's make this G so the formula, which is the gravitational constant. There's one expression. So now be F d square equals to G m1 m2 m1 m2 m1 m2. Divide both sides by m1 and m2 to make G to be on its own. So that be m1 m2. So we now have the gravitational constant will now be G is equals to F d square over m1 and m2. So this F is your force. This D can be now be length squared m1 m2. So the dimension for force in the let's make it easier. For force in the table is M from here M L T raised to power minus 2 times this distance now be L square over m1 m2 m1 m2. This is the same thing, mass cancel mass, then this mass will come up to now be equals to this m now be m inverse, then we have t used to power minus 2, so t used to power minus 2 and L square. So we can now rewrite this to say that m, or let me rewrite it here to be m inverse. Let's put this L, let me arrange it accordingly. So L square t raised to power minus 2. So the dimension for gravitational constant is m inverse L raised to power 2 t inverse. So let me solve a question which one of my fans asked me to solve on this video lesson. Is called dimension analysis, to check if a formula is correct. So let's solve that question. So someone asked me to solve. In this question, find the value of x, where k is a numerical constant. In this question, for it to be dimensional correct, this side must be equals to this side, and this F is your force, this k numerical constant, this P is your density. So let me write it. It's your density. This A is your area, and this V is velocity. So to solve this is force. Dimension for force from the table is ml. So m l t raised to power minus 2 t raised to power minus 2. This numerical constant is equals to 1. So in this case, the numerical constant will be equals to 1 times dimension of density from the question which is solved we got this dimension of density L raised to power minus 3. So to solve further, this area, told you earlier that area is length times breadth. So length and breadth are both in meters. So we therefore say length breadth equals to length, which the dimension for length is L. L times L will give us L square. So therefore times L square. This is velocity. The dimension of velocity, let's open the bracket, is L 3 raised to power minus 1, 3 raised to power minus 1, all raised to power x. And there's a x here. So let's open the bracket with this s. So it will be L 3 raised to power minus 2 equals to 1 times everything to give us the same. So L raised to power minus 3 times L square. Open the bracket. We have times L raised to power x, then t to power minus s. For it to be dimensionally correct, this side must be equal to this side. So let's collect like terms. There's length here, there's length here. So we can therefore say that L 3 raised to power minus 2 will now be L minus 1 plus x t raised to power minus x. So let's compare. There's m here, there's m here. So let's say m equals to m. The visible one is here, the visible one is here, but it has no effect in this case. So we will look for s. So what carries s is L and t. So if we solve for length and length, we will get s, and solve for t and t, we will get s. We will get the same answer. So let's solve for the value of t first. So t raised to power minus 2 in this case equals to the t here, 3 raised to power minus x. They both have the same base, so we cancel out. We then have minus 2 equals minus x. Minus cancel minus. So we can therefore say that in this case x equals to 2 using something through the time. So let's solve it through the length. We can therefore say that with the length here is equals to the length here, which is L raised to power minus 1 plus x. There's an invisible one here. Length cancel length. We then have 1 equals to minus 1 plus x. This minus 1 goes to this side. We then have 1 plus 1 equals to x. Equals to x. So in this case, s also equals to 2. So the answer to this question is s equals to 2. So s equals to 2. So the value for s in this question is that x equals to 2. So if you enjoy what you watch so far, look for the dimension of surface tension. Let me give the formula. The formula for surface tension is force over length. So if you know what I did so far, look for the dimension of surface tension and put your answer in the comment section. Force over length. Don't forget to drop the comment in the comment section. Like this video, comment, share the video to your friends who are finding it very difficult, and so don't forget to hit the subscribe button for more videos. Thank you for watching.